In this podcast, we're going to look a little bit more in depth at the radioactive particles involved in nuclear reactions. All right, the alpha particle is one. It occurs what we call alpha decay. Alpha is this little funny looking sideways little fish looking symbol. Basically, it's the equivalent of a helium nucleus. Okay, so it has 2 protons and 2 neutrons, which gives it a mass of 4 and 2 protons. It also has a charge of 2 because it has no electrons to balance it out. Okay, so those protons give it a positive charge. Here's an example of an equation where we have uranium-92 breaking down into thorium and giving off an alpha particle right here, this helium. So alpha particles can be written with either He or the alpha symbol. Either one is acceptable. Okay. Alpha particles, alpha production is limited to heavy radioactive nuclei. Basically, you're looking for anything with an atomic number larger than 60. Okay. Here's another depiction of an alpha particle being emitted. All right, the next is going to be beta decay. Beta particle is going to be basically like an electron that has been ejected from the nucleus. Okay, so it's going to have -1 protons, which gives it a negative charge, and it has no mass. You can use the E or the funny looking B, beta symbol. Here we have an example where we have thorium undergoing a beta emission right here, letting off this beta particle, and becoming 234 Pa. All right, and basically beta emission is going to convert a neutron in the nucleus to a proton. And beta emission you usually see when the isotope's mass is larger than normal. It wants to take an extra neutron out and change it and pop it out of the nucleus into a proton. And pops that beta particle out of the nucleus to try to stabilize that nucleus. All right, here is another depiction of a beta particle. Here it breaks down that the neutron is converted into a proton, a beta particle, and antineutrino right here. Okay. All right, then we have gamma ray production. Gamma ray is going to occur in occurrence with other types of radiation. So here you see a uranium that undergoes alpha decay to become a thorium and also emits 2 gamma rays. Gamma rays are basically going to be high energy photons, and like I said, they have to occur with other forms of decay, so alpha or beta. Gamma rays are massless. They do not have a mass and do not have any protons associated with them, as you see the 0 here. So by themselves they can't change the nucleus. They have to occur with another type of decay. All right, and here you see a depiction of a gamma particle. All right, the next one is going to be a positron, which is basically the antiparticle of an electron, the opposite of an electron. All right, here we see a sodium atom emitting a positron to become a neon atom. Positron emission is going to convert a proton to a neutron, so it's basically the opposite of beta decay. Electron capture is another one. It's where you have an inner orbital electron that is captured by the nucleus, and then you have a change in the nucleus. Okay, so here we have a mercury atom that captures an electron, becomes a gold atom, and emits a gamma particle. Electron capture is going to convert a proton into a neutron. All right, strength of particles. Well, here in this picture, you see that alpha is the weakest particle. We can shield it with paper or with our hand, clothing. Beta particles can be shielded with aluminum or any sheet of metal foils like gold foil, aluminum foil. Gamma rays and X-rays, right here, we're going to have lead to stop them. And the neutrons, you're going to have a full meter of concrete to stop them. Okay, here's another little summary slide. It shows us the alpha particle, the symbols, that it has low power, and that you can have paper or clothing to shield it. Beta, the little symbols, the B and the E. Medium power, metal foil to shield it. Gamma, little y, high power, Lead and concrete shield it. All right. So stability. Basically, decay is going to occur in such a way as to return a nucleus to stability. Stability is seen right here on this band line and shows us that the most stable isotope is going to be iron 56, iron with a mass of 56. If the atomic number is greater than 83, then the nucleus is going to be radioactive, always. All right, and that leads us to our last topic of decay series. So in a decay series, you're going to have a radioactive nucleus that's going to undergo several steps to get to a stable state. Okay, so here you start with this thorium atom, undergoes alpha decay to become radium, and then actinium beta decay, and then it undergoes another beta decay to become thorium again, but now we're thorium-228 instead of 232. Then it will become alpha decay and become a radium with a different mass, another alpha to become radon, another alpha to become polonium, another alpha to become lead. Then it'll undergo beta to become bismuth, another beta to become polonium, and then it can undergo alpha to become lead again, and this was where we would end. Now, on the contrary, after going from this lead and betaing to this bismuth, it could have underwent alpha decay at that point to become thallium, and then beta decay to become lead. Okay, so sometimes you'll get multiple paths, but they should all lead to the last stable isotope. Okay, now lastly, let's say I was going to be lazy and I didn't want to figure out all of this stuff. Okay, let's try to write a balanced equation to represent this decay chain. Okay, so first off we have thorium 232 and 90. So I'm going to write that out real quick. Okay, and we know that it undergoes a series of alpha, which is 4,2, and beta decay, which is 0, -1, to become the final product of, let's see, there's our final product of lead 20882. Okay. All right, so we're going to try to balance this equation. I would start on top because on top the beta is not going to affect that mass number, and that will enable us to see how many alpha decays we have here. Okay, so we have 232 equals 4x. We don't have to include this because it's 0, plus 208. All right, 232 minus 208. Okay, that gives us 24, and that's still equal to 4x, so x is going to be 6. So we have 6 alpha decays going on here. Okay, so that's 1, 2, 3, 4, 5, and 6. Okay, so either way you would have went, you would have ended up with 6 alpha decays. Okay, all right, now we can go back and find our beta decays. So now we're going to use the bottom number. So we got 90 equals 6 times 2 is 12. 6 times 2 minus x plus 82. Okay, so we got 92 equals 12 plus 82. Okay, so let's figure out what that is. All right, -4 equals -x. Then we can just change our sign, so it tells us we have 4 beta decays total. Okay, and that would be 1, 2, 3, 4 if you went this way, or 1, 2, 3, 4 if you went that way. Okay, so either way, this is the balanced equation, no matter which way you go down here. Okay, they both work.